Hello students, in this session we are going to study torque at the junction. Before writing here the torque at the junction, I have said that always compare with the direct stress problem, right? So you imagine the forces here like this. When the direct load was applied, suppose this was a bar, we have done some problem on the direct loading, and there were some forces like this, P1 on one phase, P2 on this phase, and P3 suppose here, right? So there were intermediate forces were there, right? And in that case, what we have done that we have divided this into two parts. This is one part and this is two part, and then we have found out the individual forces on the two parts or three parts, whatever is here. It is two parts, so it may be three parts. So we have divided. So at A there is only P1 force, so there would be only P1 force in this part. Just for reminding purpose I am doing here. And at and C part there is P3, and it is not common. C part is not common to any other part, so there will always be P3. So P1 here, P3 here, right? And for static equilibrium, if leftward force is P1, there must be some rightward force of P1, so that body should remain in static equilibrium. If P3 force is here, P3 force should be in left direction, so that this body, second part of the body, should be in static equilibrium. And another is that sum of this and this, P1 plus P3, algebraically sum, right? P1 is in rightward direction, P3 is in leftward direction. That should be equal to the P2, which is the force applied, right? That should be equal to this, right? Though this type of problem we have done when we were doing the principle of superposition. There were intermediate forces were there in that case, right? Similar type of situation is here. What is happening here is there is shaft at which torques are applied at intermediate positions, right? Suppose we are having, suppose a rigid support is there, and there is a shaft. Suppose this is a one part of the shaft, and there is another part of the shaft, right? This, and some torque is applied in the intermediate points, like suppose here we have applied some torque, say 2T, and at this part, at this end, we have applied suppose T torque, and this is A, B, C, right? And we want to find out the total angle of twist. In this case, what was the total deformation? So total deformation was deformation in 1 plus deformation in 2, right? So that was, this was 1, suppose this was 2. So what was that? So in that case, that will be equal to PL upon AE, and both are tensile, and tensile are taken as positive. So we will write P1 L1 upon A1 E1 plus this is P3, so P3 L2 upon A2 E2. So this is how we have obtained the total deformation in this bar. Now this is a shaft and torque is applied 2T and T anticlockwise direction here, and it has some dimensions. Say it has modulus of rigidity G1, polar moment of inertia J1, length L1, these are its configuration is given. G2 is its modulus of rigidity, J2 is polar moment of inertia, L2 is its length, and suppose this is one part and this is two part, right? These quantities are given, suppose, for these two shafts, right? Different materials are there, different diameters are there, different lengths are there, right? And torques are applied like this, and we want to find out the total angle of twist. And angle of twist formula we know. What is angle of twist formula? This is PL upon AE, it is TL upon GJ. Remember this, in previous lecture we have done this. theta, angle of twist is given by TL upon GG. Now divide this shaft into two parts. So write two parts separately, and find out the torque on each part. And both of the bodies are in static equilibrium. Means if one end of the body contains one load, one torque in one direction, suppose clockwise, then the other part will be having anti-clockwise rotation because body is in static equilibrium, right? As like here, that if P1 is in leftward direction, P1 at other end should be in rightward direction, so that this body AB should be in static equilibrium. P3 in leftward direction, so P3 should be in rightward direction, so that this body in static equilibrium. Similarly, there are some common points, this A, B, B and C. B is a common point. And at B point, common point, the sum of the forces should be equal to the force applied, P2. P2 is the force applied. So here also at C point, C is not common to any other part of this section. So torque applied is anti-clockwise direction, so it will remain T torque, right? But what will be the torque at B? And the total torque on this should be equal to 0 because static body is in static equilibrium. So if a anti-clockwise torque is applied at other end, there must be a clockwise torque so that the body may not rotate, right? The body should be in static equilibrium. So this is the torque acting on this part. This is part 2. Anti-clockwise at this edge, clockwise at point B. Now B point is a common point. So at B, the total torque should be 2T. Total torque at B should be equal to 2T. That should be clear, right? So if total torque at B is 2T, then how can we find out what is the torque remaining? Clockwise torque T already we have applied, so remaining torque will be clockwise T, right? Because the torque at B in part 2, torque at B, I am writing here, torque at B should be equal to torque at B, TB writing here, I am writing here, right? Here so the space can be saved. So torque at B should be equal to, that is 2T clockwise. Total torque is 2T clockwise. We have applied torque at B at part 1, part 2 clockwise. We have applied torque at B at part 2 clockwise. This is already applied, right? And algebraic sum of this torque and this torque should be same. So plus torque at B in part 1. In part 1 of this body, we don't know what is happening here. And that should be equal to, total torque is 2T clockwise. 2T clockwise, right? So total torque is 2T clockwise. And 1T clockwise we have already applied. So this is T clockwise. Right? So TB at 1 should be equal to 2T clockwise minus, this is T clockwise already we have found out. We have already applied at this part. T clockwise, so that 2T clockwise minus T clockwise, that should be equal to T clockwise. Right? So T clockwise already applied. There should be a T clockwise torque at B so that the total torque should be 2T. So we can apply here a T torque clockwise. So here torque is clockwise and this body is in static equilibrium. It means there must be an anti-clockwise torque so that the body may remain in static equilibrium, right? So it means the torque at part 1 is T clockwise at this point, and in this case the torque is also T, but it's that rotation is different, right? It is anti-clockwise at this part, right? And you should remember the sign convention. Nut tightening and nut loosening. If it is fixed here, this is a nut opening system. So this is nut opening. and nut opening we have taken negative, minus torque, right? And it is torque tightening, right? Nut tightening, it is clockwise at this phase. If it is fixed here, the nut is tightened, and this is nut tightening, nut tightening, right? And nut tightening is positive and nut opening is negative. So this theta 1, so we can write total angle of twist will be equal to, this is positive because it is nut tightening, minus theta 2. So this is the total angle of twist for this case, right? And what we can write is theta will be equal to theta 1, positive torque is applied. So we will write T L upon G J minus because it is negative. Torque is same, magnitude is same, T L upon G J. So this is the total angle of twist for this case, right? Where there is torque applied at this point and at this point 2T torque applied, and we have cut this part into two parts and we have obtained what is the torque at both the ends, and then using the sign conventions we are finding the total angle of twist for this case, right? So this is how the problem of torque at junctions, like this is a junction, B is a junction where AB and BC meet, B is a junction where torque at junctions are applied.